Imagine you're an astronaut, the first to set foot in a new era of lunar exploration. Stepping out onto the lunar surface, you're greeted by a breathtaking view. Earth, a vibrant blue marble, shining brilliantly in the inky black sky. A stark contrast to the desolate yet beautiful landscape around you. But to not only survive but truly thrive here, to build a home away from home, you need one thing above all else: power. The ability to harness and distribute energy is paramount. Power keeps your air breathable, filtering out harmful particles and maintaining a stable atmosphere within your habitat. Power keeps your habitat warm, shielding you from the extreme temperature fluctuations of the lunar environment, where temperatures can swing wildly from scorching heat to frigid cold. And power keeps your critical systems running smoothly, ensuring everything operates as it should, from life support to communications. It's the very lifeblood of any lunar base, the invisible force that sustains every aspect of life and work. Without it, you're just in a cold, lifeless box, isolated and vulnerable in the vast expanse of space. Power runs your computers, allowing you to conduct research, analyze data, and communicate with Earth. Power charges your rovers, enabling you to explore the lunar surface, collect samples, and expand your understanding of this alien world. And power lets you mine valuable water ice, which can be converted into fuel for rockets and drinking water, essential resources for long-term sustainability. NASA's Artemis program isn't just about briefly visiting the moon for a quick photo op. It's about establishing a lasting human presence, a permanent foothold on another celestial body. To achieve that ambitious goal, we need a power source that's not just adequate, but strong and robust, reliable, capable of withstanding the harsh lunar environment and always on, providing a continuous supply of energy, even during the long lunar nights. This is one of the biggest and most complex engineering challenges in transforming the moon from a place of fleeting visits into a true, sustainable home for humans. Do we want to be mere visitors, leaving only footprints behind, or permanent residents, building a future for generations to come? If we choose to stay, we need a comprehensive energy grid, a lunar power infrastructure that supports everything from 3D printing habitats using lunar regolith to running complex scientific experiments that unlock the secrets of the universe. The power demands are absolutely huge, far, far more than any previous short-term lunar mission could have ever required. So, what innovative solutions are on the table? What power generation options are viable in this unique environment? How do we generate enough clean, sustainable energy to not only survive, but to truly power our ambitious lunar future? Solar power seems like the obvious answer. The sun is right there, and solar panels have powered everything from satellites to the International Space Station. But the moon has a big problem. The lunar night lasts 14 Earth days. That's 2 weeks of darkness and freezing cold. Solar panels can't generate power, and batteries big enough to last are heavy and expensive to launch. Then there's lunar dust, sharp, clingy, and everywhere. It coats panels, blocking sunlight and cutting efficiency. The best spots for solar, like peaks of eternal light, are tiny and highly contested, and many promising base locations like shadowed craters with water ice get little or no sunlight. Solar will help, but it can't be our only solution. What if dust covers the panels before nightfall? What if batteries fail? For a permanent base, we need a power source that works day and night in any location. We need baseload power, a steady, reliable flow of energy, no matter what. That's why NASA is looking beyond solar. The search for a better solution is on. If solar isn't enough, what's next? NASA's answer: nuclear power. Not giant power plants, but small, safe reactors designed for space. Fission surface power. Think of it as a nuclear battery for a lunar village. We've used radioisotope generators, RTGs, for decades on probes and rovers, but they don't make enough power for a base. A fission reactor is different. It splits atoms in a controlled chain reaction, releasing much more energy. It's compact, reliable, and can run for years without refueling. A suitcase-sized reactor could generate 10 kilowatts of electricity, enough for several homes on Earth. NASA wants a system that's lightweight, robust, and can be set up with minimal astronaut help, maybe even by robots. Once running, it provides constant power day or night anywhere on the moon. This would be the backbone of a lunar power grid. It's bold, but it's exactly the kind of leap we need to become true space explorers. The future of lunar living may be nuclear. So, how does a lunar reactor actually work way up there on the moon? It's a fascinating question, And the answer lies in harnessing the very power of the atom. At its heart, it's all about nuclear fission, a process that releases tremendous amounts of energy. Imagine a big, unstable uranium atom, packed with protons and neutrons, just waiting for a little encouragement to release its energy. Now give it a nudge with a neutron, a tiny subatomic particle, and bam! It splits, releasing heat, radiation, and crucially, more neutrons. Those newly released neutrons then go on to hit other uranium atoms, causing them to split as well, creating a cascading chain reaction. In an uncontrolled scenario, like in a bomb, this happens almost instantaneously, releasing a massive amount of energy all at once. But in a reactor, we carefully control this chain reaction to produce a steady and manageable power output. Moderators like water or graphite slow down the neutrons to increase the likelihood of them causing more fissions, while control rods, made of neutron-absorbing materials, absorb excess neutrons. By adjusting the position of these control rods, we can precisely speed up or slow down the reaction as needed, maintaining a stable and consistent energy production. The intense heat generated from fission is then transferred away from the reactor core by a coolant, such as water, liquid metal, or even gas, which then carries the heat to an engine. On Earth, in traditional nuclear power plants, we typically use this heat to boil water, creating high-pressure steam that spins massive turbines connected to generators. But on the Moon, where resources are scarce, we'll likely use more compact and efficient engines, like Stirling engines, to directly convert the heat into electricity. The result is a steady, reliable, and long-lasting power source, all derived from a relatively small amount of nuclear fuel. It's a safe, efficient, and incredibly durable energy solution that can run continuously for years without refueling. This technology represents a true marvel of engineering, pushing the boundaries of what's possible in energy production. It's about turning the immense power locked within the atom into usable electricity, providing the foundation for a thriving new world on the Moon. With precise control and advanced monitoring systems, we can ensure we get exactly the amount of energy we need, precisely when we need it, optimizing resource utilization. And that's how we'll keep the lights on, the habitats warm, and the research running, even during the long and frigid lunar night. Science makes it possible, and ingenuity makes it a reality. With nuclear power, the Moon becomes more than a temporary outpost, it becomes a home. Reliable energy means life support systems always work even during the 2-week lunar night. No more power rationing, just safe, comfortable living. Abundant power lets astronauts do real science drilling, deep running advanced labs, and setting up powerful telescopes. The Moon could become a world-class research station. Nuclear energy also means self-sufficiency, using power to extract water from lunar soil, grow food, and make rocket fuel. We could 3D print habitats and infrastructure using local materials. As the base grows, more reactors can be added, creating a true lunar power grid. This is how a small outpost becomes a village, and a village becomes a city. It all starts with a reliable spark. Nuclear power is the key to building a real lunar community. The dream of living on the Moon is within reach. Building a nuclear reactor for the Moon, a self-sustaining power source on another celestial body. It's not just about assembling parts, it is a huge engineering challenge, pushing the boundaries of what we know and what we can achieve. Safety comes first, always. The reactor must be safe during every phase: launch, the perilous landing, and continuous operation on the lunar surface. Redundancy and fail-safes are paramount. The fuel stays separate and inert until it's safely on the Moon, ensuring no accidental reactions during transit. And to minimize any potential risk, the reactor is set up far from the habitat, providing a safe operational distance. It's further shielded by layers of lunar soil, or regolith, acting as a natural radiation barrier. It must survive the intense vibrations and forces of rocket launches, the jolting impact of landings, and the extreme lunar temperatures, which swing wildly between scorching heat and bitter cold. Every single part, from the reactor core where the energy is generated to the radiators that dissipate waste heat, must be incredibly tough and utterly reliable, built to withstand the harsh conditions of space. It needs to keep running smoothly for years, providing continuous power with very little maintenance required. Getting rid of waste heat is especially tricky in space. There's no air or water to carry heat away through convection, so we rely on large radiators to beam the excess heat directly into the cold vacuum of space. These radiators must be incredibly lightweight to minimize launch costs, and highly efficient to effectively shed heat, and they must be able to survive the constant bombardment of micrometeoroid impacts. The whole system has to be small and light enough to fit inside a lunar lander. Every single kilogram counts when you're launching things into space. The ultimate goal is a plug-and-play reactor, a system that's easy to set up and operate. It should be deployable either by robots working autonomously or by astronauts on the lunar surface, ready to reliably power a lunar base for a decade or more. Solving these complex engineering problems pushes technology forward in leaps and bounds, not just for enabling lunar exploration and habitation, but also for benefiting life here on Earth too. It's undoubtedly a tough journey, filled with challenges and requiring innovative solutions, but the potential payoff is absolutely huge, paving the way for a sustainable human presence beyond Earth. Safe, reliable, and continuous power is the key that will unlock long-term lunar living, making sustained exploration and scientific discovery a reality. NASA isn't just dreaming, they're building the future now. The goal, a flight-ready fission surface power system tested on Earth and ready for the Moon by the early 2030s. NASA, the Department of Energy, and private partners are racing to make this vision real. The first reactor will be a demonstration set up on the Moon, turned on, and monitored for performance. Its success will pave the way for a scalable lunar power grid. Powering a moon base is the first step to becoming a multi-planetary species. The tech we develop here, compact reactors, advanced life support, will help us reach Mars and beyond. The Moon is our test bed for living on other worlds. Soon we'll see lights on the lunar surface powered by the atom, built by human ingenuity. This is more than a power source, it's a beacon of hope and a testament to our drive to explore. The future is bright, and it's powered by the atom.